charge balance and the systematic method. So first off, only worry about this if your equilibrium actually contains charged species. If it doesn't, then you can skip this step. Let's first talk about this in terms of the following generic equilibrium. AB2 is in equilibrium with A2 plus and 2B minus. So to explain this, let's pretend that we have a 0.1 molar solution of AB2. Assuming that there is complete dissociation and looking at the mole-to-mole ratio of AB2 to A2 plus, you see that it's a 1-to-1 ratio. So if it were to completely dissociate, you would obtain 0.1 molar solution of A2 plus. But if you look at the mole-to-mole ratio of AB2 to 2B minus, you see that it is a 1-to-2 mole ratio. So you would actually obtain 0.2 molar of 2B minus. So you can't really set the concentration of A2 plus equal to the concentration of B minus because they're not 1-to-1. You have to look at it and decide for yourself how they're related. So it looks like B minus is twice that of A2 plus. So when you write that in equation form, you actually have to put a 2 in front of the A2 plus. And then you can set them equal to each other. So I think that this is totally counterintuitive. Sometimes what helps me is to look at the charge on one of the species, and that's pretty much always the coefficient that you can put out front here. So this is kind of a complicated equation to have to put into Mathematica, so something handy to do is assign variables to all the pertinent species. Notice that these are all aqueous species, so they all get variables. And to rewrite this equation in terms of variables, you would say that 2y is equal to z. And this is the equation that you could plug. Oh good, there's a child screaming. This is the equation that you could plug into Mathematica. And to show all of your work, be sure to write plus minus in parentheses. That was a generic example. Let's do something that would be a, quote, real-life example. Scoot all this up. All right, so let's do a charge balance for the reaction of calcium fluoride. This is a solid in equilibrium with calcium plus 2. Plus 2F minus. Let's assign our variables. Notice that calcium fluoride is a solid. Never assign a variable to a solid, ever. But aqueous things we can assign variables to. Let's call calcium plus 2x and F minus y. And to write a charge balance equation for that, you would simply say that 2x is equal to y using the rules that we just learned. All right, let's do a slightly more complicated example. How about some silver phosphate? In equilibrium with its ions. So you see that we have a polyatomic ion going here. If you need to, always feel free to refer to your formula page that has some common ions on it. So we expect you to know what this will break up into. So this is going to break up into 3 silver plus ions and 1 phosphate ion. Again, don't assign any variable to the solid silver phosphate, but you can definitely assign variables to the silver plus ion and the phosphate ion. So to assign a charge balance here, let's say you've got X and Y. Note the 3 minus up there, that'll help you. And you go ahead and put X equals 3Y. And this is the equation that you would plug into Mathematica. Let's do one last example that's even more complicated. Pretty soon we're going to be using more than one equation to describe equilibrium. So let's show you how that works. Let's work with a 2-equation system. HNO2 plus liquid water can be in equilibrium with hydronium ion H3O plus and NO2 minus ion. Whenever we do these acid-base equations, there's also going to be the autoionization of water, equilibrium occurring simultaneously. So the autoionization of water looks like this. You will soon have this memorized, I promise. Right, so 2 molecules of water dissociate into hydronium ion and hydroxide ion. So pretty soon we will learn how to assign variables to systems like this, but we can assign X to HNO2. Liquid water we're not going to do anything to because it's not an aqueous species or a gas. H3O plus we're going to call P, which stands for proton. NO2 minus, let's go ahead and call Y. Liquid water we don't do anything to. H3O plus again we'll call P, and OH minus we'll call H for hydroxide. So to write the charge balance here, we'll put all of our positive charges on the left and all of our negative charges on the right. So let's look for our species that are positive. Looks like we only have the H3O plus that are positive, and those are just the P, so we'll just write P with nothing in front of that. P is equal to the negative charges. So it looks like we've got NO2, screaming child outside, and OH minus. So that looks like it'll be Y plus H. And that is the equation you would plug into Mathematica. Let's do one more example. We've got calcium fluoride. That's a solid in equilibrium with calcium plus 2 and 2F minus. Our second equation is calcium nitrate with a single-headed arrow going over to calcium plus 2 and nitrate ion. Let's assign variables. We won't do anything to the calcium fluoride since it's a solid. It's called calcium plus 2X. There's another X down there. F minus can be Y. We're actually not going to assign a variable to calcium nitrate because if you go look at your solubility chart, it is a completely soluble salt. All nitrates are, so we're not going to do anything to it. And then we'll call NO3 minus RZ. When we set up a charge balance for this, it'll look like the following. Plus minus, we'll put all of our positive charges on the left. We will put 2X, not because there are 2 calcium plus 2 ions, but because of that positive 2 charge. 2 plus is going to be equal to the sum of our negatively charged ions, so Y plus Z. And this is the equation you would plug into Mathematica.